So our next speaker is Desmond Rayford from the Geological Survey of Ontario. Desmond has a degree in geology, geophysics, and GIS. He has worked in mineral exploration for 20 years, exploring for precious and base metals in Canada, in the United States, and overseas. He is now senior geophysicist for the Ontario Geological Survey. He will present to all of us a history of the Ring of Fire.
Thank you. Good morning. So this is the first of two talks on geophysics in the James Bay lowlands. Scott Hogg, one of my co-authors, is going to be presenting later in this session. The topic of this presentation is the role of geophysics in the CHROMITE discoveries. So for those of you who are not familiar with Ontario geography, the so-called Ring of Fire is located in a very remote area of the province. There are a number of First Nations communities in the area. They're serviced only by air and for a couple of months by winter road. The other thing you should know is the area is very flat, very swampy, and there's almost no outcrop. So we'll start with some geological context here. The green colors on the map on your left are the greenstone rocks of the McFaulds Lake greenstone belt. It's been dated 2.7 to 2.83 billion years old. It's an Archean greenstone belt. Partially obscuring the McFaulds Lake greenstone belt, particularly to the east, is a layer of Paleozoic sediments, predominantly limestones, and overlying all of this are unconsolidated quaternary sediments to a depth of several meters. The pink and yellow colors that you see outside the greenstone belts are granitoid batholiths and plutons. So we're just going to zoom in to the inset area in the center of the figure here and look more at the deposit geology. The hashed area shows the outline of the Paleozoic cover rocks. These are the limestones that partially obscure the underlying Archean basement rocks. There are two important intrusive complexes, the Double Eagle intrusive complex to the southwest and the Black Thor complex to the northeast. And these are layered ultramafic sills. They would have been deposited roughly sub-horizontal. They've now been rotated into the near vertical. And these host the CHROMITE deposits that have been discovered so far. And those are noted with the two-letter codes. So we'll take a quick look at a cartoon of the stratigraphy. Starting at the bottom, we have the oldest Archean basement rocks. They're cut in places by feeder dikes. And overlying this is the intrusive complex, which is the layered ultramafic intrusions, and within that are hosted the CHROMITE horizons shown in black. At the top of the intrusive complex is a gabbroic unit, and then in the hanging wall we have the mafic and felsic volcanic rocks and ferrogabbros. So just summarize the discovery history. The first indication of CHROMITE mineralization was intersected while drilling a ground EM anomaly in 2006. Free West did the work. They found no sulfides to explain the EM response, but what was noted were two 1-meter bands of CHROMITE mineralization, and the geologists were astute enough to recognize the significance of this, and that ultimately led to the discovery of the Big Daddy deposit. The following year, Noront went on to discovered 2 magmatic sulfide deposits, the Eagle's Nest and the Eagle 2. Black Thor was intersected in 2008 by Free West, drilling on a 3.5 kilometer gravity anomaly. Blackbird was intersected by Noront when following up on the Eagle's Nest and Eagle 2 deposits. Black Label was intersected during the exploration of targets in the Black Thor footwall. Black Creek was found by probe mines along strike from Black Thor. And finally, the Black Horse deposit was intersected by Fan Camp while drilling deep nickel, copper, platinum targets. So the resource estimates are summarized here. What you should know is that the mineralization, the chromatite mineralization varies from a few meters up to over 100 meters, and typically it's in the order of tens of meters. So a good place to start with considering the geophysical responses of the deposits are the physical rock properties. And this is a compilation of over 1,000 outcrop and drill core measurements of magnetic susceptibility. And as we often see with magnetic susceptibility, there's a large range within rock types, and there's also considerable overlap between rock types. That said, we do see some increase in magnetic susceptibility, the median susceptibilities of the ultramafic rocks towards the bottom of the figure. Moving on to the specific gravity measurements, as we might expect, we see a much better differentiation between rock types, moving from the more felsic compositions at the top of the diagram. Densities increase progressively towards the more mafic compositions as we go further down. Again, as we would expect, and it's not surprising because density is a bulk property as opposed to magnetic susceptibility, which is really a measure of magnetite concentration, which is usually just an accessory mineral. What is surprising here are the anomalously low densities of the ultramafic units towards the bottom of the figure. And this is ascribed to the effects of alteration, serpentinization, and calc carbonate alteration. And then at the very bottom, we see that the chromatite ore samples return high densities, much higher than any of the associated country rocks. So that would lead us to suspect that gravity might be a good exploration tool. The electrical property information in the area that's accessible is a little sparse, but this is from a downhole IP resistivity survey done by JVX in the area. And we're looking at apparent resistivities, and we see a 4 orders of magnitude decrease in apparent resistivity over the ultramafic units, the peridotites, as opposed to the country rocks, the granodiorites either side. And this is confirmed, as we'll see, with the EM responses that we'll look at in a moment. So let's look at the deposit responses themselves, starting with magnetics. We have ground data on the left, 1VD airborne on the right. And we see that there's a well-developed magnetic response to the northwest of the chromite horizon, shown in black. Those are the ultramafic footwall rocks, and that's consistent with what we saw with the magnetic susceptibilities. We also see a bit of an offset in the magnetics, about 500-meter offset, which suggests that the Big Daddy, Black Creek, and Black Thor mineralization all lie along the same offset horizon. So the results are very similar between the ground and the airborne magnetics. When we look at the gravity, again, ground on the left, airborne vertical gravity gradient on the right. The filtered ground data, high-pass filtered ground data, shows a pretty good correlation with the gravity highs and the surface projection of the mineralization, again, as we might suspect from the physical property measurements. It's the situation with the airborne gravity is a little less clear. There's a bit of an offset. And from forward modeling that's been done, we see that the airborne gravity gradient really doesn't have enough sensitivity to unambiguously identify the chromite mineralization. Instead, probably what we're seeing are the higher density hanging wall rocks, the mafic volcanics, and the ferrogabbros. So moving on to EM, we're looking at horizontal loop EM profiles. This was a survey that was carried out to follow up an early geothermal survey in the area. And we're actually looking at the discovery hole. So we have a decent looking ground response. A hole was put down. No obvious source of conductivity was found, but the chromite horizons were identified. And almost certainly the conductivity is associated with altered ultramafic horizons. So after the initial geothermal survey had been flown, various other airborne EM systems were flown over the area, aerotherm, VTEM, ZTEM, and they all picked up similar responses, parallel with but offset from the chromite horizons. And this is, we're looking at the aerotherm data. The conductivity response is again associated with the footwall rocks, the ultramafic sills, in other words. And we have a good early and late time responses with a slightly offset magnetic response, as we would expect. So we're going to step back here and look at how geophysics can help us with the regional interpretation. In the top left, we have an extract from an older geology map. Bearing in mind there's very little outcrop in the area, it has relied to quite a large extent on the existing aeromagnetic data at the time. And we have two light blue units. These are the shown as mafic intrusive rocks. And looking at the magnetic, total magnetic field below, we see this, it's probably looks like a reasonable interpretation. However, when the airborne gravity gradiometry survey was flown, we're looking at the vertical gradient in the bottom right. We see right away that while we have a good density response from the southeast mafic unit, there's nothing like that to the northwest. So clearly that was misinterpreted. So using this kind of data, plus a whole host of data that's become available from companies and all the work that's been done in the area, the geological map was revised and published earlier this year by Riku Matsuranta, who's one of my co-authors, and Michel Houlet from the Geological Survey of Canada. So moving from the qualitative to the more quantitative interpretation, this is work done by Peter Diorio, who's one of my co-authors, using the McFalls Lake aeromagnetic and gravity gradiometer survey. He's inverted the results for density and susceptibility, shown here. And then what he's done is extracted depth slices from those models, used a two-color imagery, which we see on the left-hand panel, and it gives actually a pretty good representation of the geology shown on the right. Obviously, there's some cross-pollination there as well. He's taken this a little further with a classification system, and we're looking at a synthetic scheme here just to show how it works. There's a two-layer plunging antiform with different physical properties. They've been forward modeled in the center, some noise added, and then inverted for susceptibility and density. The next step is to create a cross plot of the data, magnetic susceptibility against density. And this is a scatter plot here with the red dots showing the actual physical properties of the model. And we might hope that those points would cluster around the actual values. What we see instead is this spray pattern. And that suggests that maybe some sort of radial classification scheme might be appropriate. And here we have a cross plot, again, density against susceptibility of the McFaulds Lake data from a depth slice, which has been divided into various zones, color-coded and numbered. Those numbers and colors have then been transferred to this image. And we see there's a pretty good correlation, even though it's a pretty arbitrary classification scheme, between known geological units, known and inferred geological units to the bottom right. So this is really just a proof of concept. The classification schemes could certainly be improved, and potentially another parameter might be added, something like conductivity. So before I wrap up, I just want to take a minute to look into the future, which is always a dangerous thing to do, particularly in this area. And perhaps there'll be an update in 2027. So far, of the 6 deposits, the 6 chromite deposits that have been discovered, 5 of those are near surface. There is still some potential for near-surface discoveries from some satellite ultramafic intrusions, but it's likely that we'll need to be looking deeper in the future. Nothing surprising in that. As we look deeper, we're going to lose the surface signal of the gravity responses from the chromites. So it's likely that the focus will need to be on the host rocks, the conductive layered ultramafics. There's an increasing amount of lithogeochemical data becoming available from all the drilling that's been done in the area. Potentially, something can be done with that to vector towards mineralization and identify fertile host rocks. And then again, there's room through things like modeling and classification or these integrated Earth models to better our understanding of the geology using all the geophysical data that's been acquired. So just wrap up here. Excuse me. So this is an increasingly rare modern example of a polymetallic mineral camp being discovered in virgin territory. 6 world-class deposits were discovered in a short 6-year period, and that was because there was an intense burst of activity. A lot of companies were involved, a host of geoscientists, technicians, drillers, and others did a tremendous amount of work in the area. The the second reason for the success was there was an early understanding of the physical properties and therefore the geophysical responses of the mineralization, the chromite mineralization that was serendipitously discovered, and the exploration focus was turned towards taking advantage of the very amenable physical properties and the conventional geophysical methods that would use those physical properties. And I'd just like to point out that while the initial discovery of chromite was in 2006, there was a stream sediment survey published in 2003 by the Ontario Geological Survey, which showed highly anomalous chromite values down ice from the now known chromite deposits. So I think that illustrates how important it is to make use of all the available geoscience data, and it's kind of the theme of this conference is data integration, because that can help fast track towards discovery. And with that, I'd like to acknowledge the contribution of individuals and companies who've worked on aspects of this presentation. Much appreciated.
We've probably got time for a question from Desmond, if there's something snappy.
Alan? Stream sediments, yep. As Dave Crabtree published 2003, it's MRD. Yep.
One more? Thanks, Desmond.
Okay.
Great.
Cheers. Great.